So back to stresses and beams. And the idea is that the total stress tensor is going to be equal to the stress tensor due to tension or compression, plus the stress tensor due to the bending moment, plus the stress tensor due to shear force, plus the stress tensor due to torque. This one we've already done. That was the simplest of them. Now we're going on to stress due to bending moment. These, in our examples, are both going to be XX stresses. This is only going to be an XY shear stress, and this is only going to be shear stress, but it has a few options. So now we're going to stress due to bending moment. Once we know that, we'll be able to give all of our normal stresses. But that doesn't mean we'll be able to, we won't have a full stress tensor. And we also won't have the principal stresses because, the shear stresses kind of, they affect what you would get when you took the eigenvalues. But we will be able to come up with all the normal stresses after this. The stress due to tension was pretty general. Didn't require a lot of assumptions about the beam. In fact, we didn't talk about any. So it didn't require beam assumptions. But the stress due to bending moment does. So yes, I am. So the overall assumptions that we make about the materials and stuff don't have anything to do with the shape, really. I guess they do sort of indirectly when you say small deformations, but so these are additional assumptions that we have to make. So these are 3 assumptions required for the stress tensor due to the bending moment. And Aaron, can you tell us anything that people should remember about this list? About this list of assumptions that I'm about to give? Practically speaking, is we'll come back to Aaron later. What Aaron would have said is that this list of assumptions is a good set of things to be ready for to appear on a quiz. Okay, so the first one is the beam has to be straight or close to straight. Must be straight or nearly straight. It's all small deformations, so there can't be much difference between those two for our overall assumptions for the class. So the way this is going to, so here's the can do, and here's the can't do. So I'm going to draw pictures for each of these. So we can do this. We can also do this. That's pretty close to straight. But as you get farther from straight, the assumptions that this math is based on get worse. So we can't do like the curved part of a hook here. Okay. Yeah, I'm not going into the derivations of these formulas we're going to use, but the derivation depends on things that would not hold for this hook. So you can't use this technique to calculate the stress due to bending moment in this hook, but you could do it for something gently curved or straight. Yeah. Then the second assumption is that it has to be prismatic. Or nearly prismatic. So you can do prismatic means cross section is the same the whole way along. So you could do something like this, but you couldn't do something like this. Can you picture what I'm talking about there? You also couldn't do something, come on. You also couldn't do a shape that's like a circle on one end and a square on the other end and blends between those two. That's not prismatic. Mm-hmm. Yeah. Yeah, so that it just means that the cross section's the same at every step along. So the whole time, like at every stop along this length, the cross section is square with the same dimensions. At every stop along the length of this, it's still like a square or rectangle, but the dimensions are changing and they're changing fast. A rule of thumb on that is sort of 10-degree difference. If you're looking at it from the side, if you know a perfectly prismatic thing, those lines are horizontal. Nearly prismatic is something where that angle is less than 10 degrees. Okay. That's right, but it does affect. So the calculations are based on assumptions about how shear stresses are developed and how the warping of each cross section happens, and those, if it's far from prismatic, then those assumptions are invalid. That's how it comes up. No, it's not just area, right? And the third, last one, is that the cross section has to be symmetric about the y-axis. Okay, so here is a pretty wacky cross-sectional shape. But with the coordinate system that we're using, the z-axis is horizontal, the y-axis is vertical, and the line of symmetry of this shape is the y-axis. So that's okay, even though that's, a pretty crazy shape. This is not okay. Because here our y-axis is like this, z-axis is like this, the line of symmetry, well, there's the z-axis. line of symmetry is parallel to the z-axis, not the y-axis, so that's no good. Yes, that's a really good question, but we are always doing our bending about the z-axis. So that's the problem. But and so really what it is, it doesn't require that. So the important thing really isn't the relationship between the y-axis and the line of symmetry. Really the important relationship is between the axis of bending and the axis of symmetry. They have to be perpendicular. The y-axis is easier to remember. For what? That's a cross section. So that thing could, so this could be a mile long. It's just that every cross section looks like this. So if I turned it, it would be a long beam with that as the cross section. The long axis of the beam is always the x-axis. So if you see anything in the YZ plane, you know you're looking at a cross section. Yeah. For the third one, you mean? No, it doesn't, because we always set it up where the axis of bending, the axis that it's bending about, is the z-axis. And to understand, so it seems a little weird off the top of your head to think that bending a beam causes stress in the x, causes an x normal stress, right? Like you have a beam like this. You apply a force here, and the fact that this bends down, and somehow that bending down of this thing causes a tension or a compression of this material along the long axis. So how does that work? How does this produce tension compression in the x direction? Where, remember, the x-axis has to be along the beam's axis, so this would be x, this would be y. Well, the answer comes from the world of track and field, like most things do. Okay, so there's 100 meters, the curve of a track. And you're gonna, for some reason, you're racing 100 meters against someone on the curve, okay? You're racing the curve. Do you want the inside lane or the outside lane? And why do you want the inside lane? Yeah, inside or outside lane. You want the inside lane because it's shorter. The distance along the inside is shorter than the outside. Well, in track meets, they stagger the start, so it's not really a problem. But that means that this distance here is shorter, and this distance is longer. Okay, so when you bend a beam, it goes from this, and I'm going to do an exaggerated picture, to this. Okay, it doesn't do it that much, or else the small deformation assumption wouldn't be met. But when it bends like that, in this case, the top is now shorter. And actually, I'm going to say that black is like the middle. Oy, oy, oy. Okay, so when you bend it, I'm going to do it like this too. The top in this case is shorter. The bottom is longer. And the black in the middle, somewhere in the middle, has to be the same if one part is shorter and one part is longer. And so that means that the part that gets shorter, well, what kind of stress leads to, I mean, that's getting shorter in the x direction. That means that there is a negative strain, right? So negative strain. If the bottom is getting longer, that means there's a positive strain in the x direction. And so the shorter part, the only way you can produce a negative XX normal strain is compression, a negative XX stress. So that's in compression along X. And the longer part has to be in tension along X. And so there you go. If you just think of it in terms of the track thing, you know, like the inside of the turn is shorter than the outside of the turn. Mm-hmm. No, we are, those are different points on the body. And so what happens at one has no effect on what happens at the other one. So you're right that it's small deformations and the amount of shortening and lengthening is really small, but that depends on the shape of the beam. It can work out that way, but either way, it wouldn't affect how you calculate this. Yep. Question? Oh. Oh. Oh, okay. Does it feel better though? Okay. Let me know if you. Okay. Now, the line in the middle it doesn't have to be geometrically in the middle, really. The line in the middle somewhere that stays the same length. Is called the neutral axis. It's really a surface, but it is an axis in the YZ plane. So that's why we call it the neutral axis. And when you're on this neutral axis, the XX stress is equal to 0. There's no lengthening or shortening, so there's no normal stress. One thing to notice now, this is another good quiz question. I would ask Erin whether it was, but she's probably stuffing her face. When we calculated the stress due to tension, it didn't matter where you were on the cross section. Didn't vary high, or let's say didn't vary along the cross section. Along the cross section, on the cross section. Didn't vary over the cross section. That cross section is the YZ plane. It only varied along X. Okay, so different X values, different locations along the long axis of the beam, you could have different stresses due to tension. But once you chose one slice, one X value, at a single X value, at the top or the side or the bottom, all of those stresses were the same. Okay, that's different with bending moment and all of the other kinds of stress we're going to deal with too. The stress due to bending moment is different at different locations on a single cross section. So what that's saying is, if you choose a single X value, like right in the middle here, say that's the X value you choose, you'll have one stress tensor corresponding to compression at the top. You'll have a different stress tensor at the middle corresponding to 0, no compression or tension, and then you'll have another one corresponding to tension at the bottom, and everything in between those will vary. So in order to do, so that's intuitively what happens. Now, to do the calculations, I need to define two mathematical things. So for the calculations, we need two mathematical definitions. The first one is the neutral axis. I said, intuitively what that is, but we need a way to calculate where that is. And the second is the area moment of inertia. And this is the thing that I said in dynamics, not to confuse these. It's really easy to confuse them because all the notation's the same. A lot of the math is the same, but they mean different things, totally different things. Okay, so the neutral axis. So if this is the beam, the coordinate system is like this. The x-axis is along the beam, the y-axis is up, and the z-axis is horizontal. And the neutral axis is parallel to the z-axis. Well, in fact, we're going to choose where to put the z-axis based on where that neutral axis is. So neutral axis is always going to correspond to the z-axis. But that doesn't really tell us where the neutral axis is. That just tells us where we're going to put the z-axis. And all you need to know to place that neutral axis is you know that it goes through, well, you know it's parallel to the z-axis. You know it's horizontal. And the only other thing you need to know is where it's placed up and down, you know? And it's always placed up and down so it goes through the centroid of the cross section. So the up-down position is given by the fact that it crosses, by crossing it through the centroid of the cross section. So for example, in this case, let me give some dimensions. So let's say that this height is 0.1 meters and this distance is 0.15 meters. Then that rectangle looks like this. Our coordinate system is going to be positioned with the z-axis going through the centroid. This is the neutral axis, and we know that the distance between the neutral axis and the z-axis and the top is 0.05 meters because of the centroid. And then this doesn't really matter, but we'll always put the origin. The origin is always going to be on the centroid of the shape, so 0.075 meters. Okay, so that was pretty easy. Any questions about that? I think a lot of times the hardest thing with these is just turning your head around into like, okay, now we're looking at the XY plane, now we're looking at the YZ plane, And then the next definition is the area moment of inertia. And here's what to remember. This is called, when people talk about this, they don't tend to say area moment of inertia. They tend to just call it the moment of inertia. And in addition to that, we're going to denote it with a capital I sub A. That's great. And in addition to that, there's a parallel axis theorem for it. I know it's so weird that it just is dumb, but this is how it is. In dynamic, yeah, I mean, you only have one in this class and one in dynamics, but they're different. They have different definitions. I'll give the definition in a second. In dynamics. Okay, this is the only one in this class. So this is, people call it the moment of inertia, and they denote it I sub A, capital I sub A, and there's a parallel axis theorem, but this isn't the moment of inertia with all those properties from dynamics. It's a different kind of moment of inertia than in dynamics. And I don't think you've taken dynamics yet, right? Oh, somewhere else. Okay, so this is different than the moment of inertia that you used in dynamics, even though it looks almost identical in the way it's used, you know. That's right. This isn't the mass moment of inertia. But you know, every confusing thing like that in engineering, you can think of as like an opportunity. And it's an opportunity to make other people feel dumb. And so, like, you will have classes where someone you're working with is going to confuse one for the other one. And it's just, often it's going to be at a time when they're emotionally vulnerable because you have a test the next day or something. And it's, yeah, exactly. And so don't think of it as like a pitfall. Think of it as like a way to, time to attack. Very good. Yeah, it's like when you're playing tennis and like, yeah, well, I was going to say, it's like, don't think of it like, don't think of it like deuce is time to relax because you can't lose on this point. It's time to win this game. You know what I mean? Or don't think of add in when you have the advantage. Don't think like, oh, I can lose this point and still deuce. It's time to win the game, you know? That's how to think of this. I know. There is a lot of stuff. But this is one more that you definitely need to remember. Okay, so definition. It has an integral definition, just like mass moment of inertia does. That's why they have the same name. Moment is a mathematical thing. This is a second moment, just like the mass moment of inertia is. And anyways, the area moment of inertia about an axis is the integral over the entire cross section of y squared dA. Yeah, where y is the vertical distance from neutral axis to the infinitesimal area dA. Anyone happen to remember what the mass moment of inertia definition is? Don't read it. It looks a lot like this, except it's a dm instead of a dA, and instead of being like a vertical distance only, it's a pure distance. It's like rho squared dm, I think is, or r squared dm possibly. Yeah, it's in dynamics, it's a resistance to angular acceleration. Here, it's a resistance to bending. So it's a measure. If you want like a suggestion for how to use it, sometimes like subtle attacking hurts more, so like you might want to just be like, when they mix those two things up, you might want to be like, oh, you didn't take dynamics, or like you didn't take deform, because like that's a good way, because it suggests that like if they, yeah, right, exactly. It's sort of like gaslighting, Yeah, you're sort of messing with their view of reality, After class, I'll give some examples. But the area moment of inertia is a measure of a cross section's ability to resist bending deformation. Okay, so I'm going to do an example here. So, piece of paper. If I turn it like this, so imagine this is the beam. You're looking at the x-axis of the beam. It's really easy to bend if I have it in this orientation, right? So this, when you're looking at the paper like this, it has a very, very low area moment of inertia. But when you look at, now this is the x-axis of the beam. Now it's really hard to bend, I mean, without flexing the paper, it's, So now what you have is a very high, relatively a high bending moment, area moment of inertia. Okay. So that's what we're talking about. And I want to do one integral example. You don't, just like with mass moment of inertia, you're never going to use the integral definition. We're going to use formulas instead that you derive from the integral definition. Yep. Yeah, you probably, I mean, I would guess like in Calc 2, or did you say Calc 3? 3, okay, so, yeah, I could see you using these as examples of multi-dimensional integrals in Calc 3. Yeah. Yeah, right. Yeah. Mm-hmm. Mm-hmm. But yeah, a moment has a mathematical definition. A moment is like, it's an integral with, I don't know. It has to do with an integral from an element, times something about the displacement from the from like a center to the element. This is the second moment because you have this thing squared, but you can have first moments too. And so yeah, a moment is just a mathematical thing. It turns out that mass moment of inertia is a way to use that mathematical thing to in physics, and area moment of inertia is a way to use that mathematical idea in D-form. So we're going to calculate the formula for the area moment of inertia for a rectangular cross-section. So we're going to find the area moment of inertia for a rectangular cross-section where the height is h and the base is w, width. Okay. First, we have to choose where origin of our coordinate system goes, and we're going to put it right at the centroid. So the z-axis is like that. The y-axis is like that. That's the centroid because that's how you determine where the neutral axis is. And now we have to, like, kind of the main trick in any kind of, using any kind of integral definition is figuring out how you're going to break your object up into these infinitesimal pieces. What we're going to do is choose these infinitesimal pieces where everything in this infinitesimal strip is the same vertical distance from the neutral axis. So we're going to do strips like this. We'll say that that has a thickness of dy. And it's at a distance y from the neutral axis. And then the definition of the area moment is the integral of, so we need to have y squared times the area of this strip. So we have y squared. What's the area of that strip? W times dy. And then we're going to integrate it from negative h over 2 to positive h over 2. You can pull the w out, that's a constant, and you get this integral. And that gives you y cubed over 3, I'll put the w in there, evaluated from negative h over 2, h over 2. And so IA is equal to W H cubed over 24. 3 times, so 2 cubed is 8 times 3 is 24. And then minus negative W H cubed over 24. And your final answer then is W H cubed over 12. Yep. And so you'll just use this formula. But M is replaced with A. M. they're going to look similar, I guess. I don't think it doesn't look exactly the same, I don't think. But they do, yeah, they do look similar, and that really causes more confusion than it helps you, you know. We use deform and dynamics. I mean, you just have to do the two parts separately, kind of. Okay, so what is this physically? This is the quizziest day in this class in a long time. So quizzy. Yeah, exactly. It could be multiples. Yeah, it's quiz warnings. 75 or 80% of the year. Yeah, that's a quiz warning. Well, now you know, though. Yeah, that's what I should say. Quiz warning. Well, anyways, now you know. So notice that the height of the rectangle, let's even just say the height of the cross-sectional shape, is much more important for I sub A than the width. You can see that from the formula. Whatever the height is gets cubed, so the effects of the height are magnified a lot in importance when you're calculating that moment of inertia. The width is just linear, so that doesn't matter as much. And that's exactly what we saw with this, you know. If it's bending this way, the area, the cross-sectional area is the same in either case, right? It's the same material. But here you have a super low moment of inertia because you have a super small height that you're cubing in that calculation. Here you have a high moment of inertia because you have a small width, but a really big height, and that big height is what you're cubing. For a circular cross section, you could do a similar calculation. So let's say a cross section with radius r. Then the moment of inertia about the neutral axis is pi r to the fourth over 4. And the last thing, just the units. You could get this from the integral definition, but the SI units for area moment of inertia are meters to the fourth. Yep. Yeah, but I don't. These are the only two formulas we're going to use. We can build up the moments of inertia of more complicated shapes with sort of a sum formula, the same way we could in dynamics. And so that's the next thing I have to talk about. In order to do that, you need to use a parallel axis theorem, just like we did in dynamics. And so I have to talk about how parallel axis theorem works with this. Okay, that's all.